Hello students, welcome back. In this part of lecture we are going to discuss about the types of satellite, energy of satellite, speed of satellite, also time period of satellite. We are also going to calculate the escape velocity of particle thrown from any planet. So let's get started. Hello students, we have already studied Kepler law in previous part. Now we are going to study the application of Kepler's law. So we are going to start. The next topic is planets and satellites. Planets moves around the sun in elliptical orbit due to gravitational attraction force. But the difference between semi-major axis and semi-minor axis is not large. So the path is, let us consider the path is as circular. Instead of path or orbit is considered as considering as ellipse, we are going to consider this orbit as a circular, since the difference in semi-major axis A and semi-minor axis B is approximately negligible. So this is the sun and this is the planet, and this is the mass ms of the sun. M is the mass of planet and the radius of this circular path is a, and v is the velocity of the planet. So the speed of the planet can be found by gravitational force is equal to centripetal force. So gravitational force is between sun and planet is g m1 m2 by r square. Here distance is not r, here distance is a. So a square is equal to centripetal force is m v square by a. So we can solve this and we will find v. V is equal to under root gms by a. This is the speed of the planet. Now time period of the planet. We know that time period is equal to 2 pi by omega, and omega v is equal to r omega, and we know that in previous slide v is equal to under root gms by a. So we can find omega. Omega is equal to, here not r, here a, okay, because a is the radius. So omega is equal to under root gms by a by a. It can be written as under root gms by aq. Now put this omega, value of omega in time period. So t is equal to 2 pi by under root gms by aq. Now squaring both sides, t square is equal to 4 pi square by gms into aq. So this is the formula, and here hence t square is equal to 4 pi square by gm into aq. This is the time period of the planet when path is circular. If path is not circular, we will take it here, instead of radius we will take it as semi-major axis. Now total energy of the planet. We know that total energy is equal to kinetic energy plus potential energy, and kinetic energy is equal to half mv square and potential energy is equal to minus gms m by a. Okay, so total kinetic energy of the sun planet system E is equal to minus gms m by 2a. We have to add both kinetic energy and potential energy. E is equal to kinetic energy plus potential energy. If you add these two equations, we will get this. E is equal to minus gms m by 2a, where a is the radius of the circular path. Okay, for Earth satellites in circular orbit, a is equal to r earth plus h. So this is the circular orbit. This is the circular orbit. This is the Earth and this is the any satellite. So this is the H, okay, and from center this is RE, okay, and we are considering this as A, therefore A is equal to RE plus H, okay. So A is equal to RE plus H in case of Earth, and radius of Earth is equal to 6400 km, and mass of Earth is equal to 6 into 10 to the power 24 kg. Now therefore total energy of the planet is equal to minus GMS m by 2a. Now the question is, a Mars satellite moving in an orbit of radius 9.4 into 10 to the power 3 kilometer, and here this is the radius, therefore we can write it as A, okay, and takes this second. So this is the time period to complete one revolution, that, and this is the time, so this is called time period. So calculate the mass of the Mars. Apply this formula. T square is equal to 4 pi square by gm into aq, okay. Your time period is equal to 27540. We are putting this in second. 4 pi square, the value of g is 6.7 into 10 to the power minus 11. The value of, we have to find the mass of the Mars, so we don't know m, okay. aq, value of a is value of radius, so 9.4 into 10 to the power 3, and this is in kilometer, so we have to convert in meter, so that's why we are multiplying 10 to the power 3, so this is whole cube. Now we can find this m is equal to, calculate, and we will find this in kg. So that's all this question. Now geostationary satellite. Satellites in circular orbits around the Earth in equatorial plane with time period of 24 hours about its own axis is called geostationary satellite. Means a satellite which revolves in equatorial plane and with a time period of 24 hours about its own axis. Such satellite is called geostationary satellite. And since the time period of such satellite is 24 hours and the time period of the Earth is also 24 hours, so if such satellite is viewed from the Earth, then it looks like stationary. Inset group of satellites sent by India are geostationary satellites widely used in telecommunication in India. Okay. Inset group of satellite is an example of geostationary satellite widely used in telecommunication in India. Polar satellites. Polar satellites go around the poles of the Earth from north-south direction, whereas Earth rotates in its axis and in an east-west direction. So here this is the axis of the Earth, rotation of the Earth, and this is the rotational direction. So Earth rotates about this axis, and this is the polar orbiting satellite, and this is the polar orbiting satellite, and it revolves from pole to pole, from north pole to south pole, okay. And whereas geostationary satellites orbits the Earth in time period of 24 hours in equatorial plane, whereas time period of polar satellites is about 100 minutes, so it crosses any altitude many times a day, and the height of the altitude of the polar satellite is about 500 to 800 kilometers. Now escape velocity. Suppose an object is thrown initially with a speed of u is equal u. this is the, this object is thrown with velocity u from a point at distance. This is the, this is the earth. Okay, so this is RE and object is thrown from here, so this is the H. Okay, so suppose the object is thrown initially with velocity u from a point at a distance RE plus H. RE plus H, this is the total distance. Okay, from the center of the earth to infinity. It's not returning, it's going to infinity. Okay, let W denotes gravitational potential energy of the object at infinity. Therefore, the total energy of the projectile initially will be kinetic energy half mu square, since u is the initial velocity of the object. So half mu square is the initial kinetic energy. Potential energy will be minus g m1 m2 by r. So here g me is the mass of earth, m is the object which is thrown, and the distance is RE plus H here, plus gravitational potential energy of object at infinity. This is the total energy of projectile at initially. Now total energy of projectile at infinity will be, if v is the speed at infinity of the object projectile, then half mv square plus w. This is the total energy of the projectile at infinity. Now, by the conservation of mechanical energy, total energy initially is equal to total energy final. So half mv square plus minus g mem by re plus h plus w is equal to half mv square plus w. Now w will be cancelled, so half mv square plus minus g mem by re plus h is equal to half mv square. So this is the right side RHS, and kinetic, this is the kinetic energy only. So kinetic energy always greater equal 0, always greater equal. If RHS is greater equal 0, then LHS must be greater equal 0. So this will also greater equal 0. So using this equation, u is greater equal under root 2g me by re plus h, and for equality, for minimum value of u, there must be equality, and that is u minimum is equal to under root 2g me by re plus h, and at surface h will be 0. Therefore u minimum at surface is equal to under root 2g me by re. If we multiply re from re, numerator and denominator, then g me by re square can be written as g naught. So 2g naught re. This is also the u minimum at surface. Now question 2. A object is fired vertically upward from Earth's surface, and it goes to a maximum height of 66400 km. Find initial speed of the particle. So let us consider this figure. This is the Earth, and initially here, this is the object initially at h is equal to 0. So this is re. Okay, initially. And finally this is the height 6400 kilometer. This is the final position. Now in this case we have to conserve the mechanical energy. So initial total energy of system will be half mu square plus minus g m earth m by, what is the distance initially, re, so only re. Okay, plus w, and final total energy of system is equal to half mv square plus minus g me m by final position re plus h. So re plus H, okay, plus W. So W will be, okay, this is the W, okay, leave it. Now conservation of mechanical energy. Conservation of mechanical energy, both will be equal. So half mu square plus minus g m e m divided by re plus w is equal to half mv square plus minus g m by re plus h, okay, plus w, okay. So w cancel, and maximum height, this is the height is attained at maximum, so at maximum v is equal to 0, okay. So this part also 0. So we have to solve this, and we will get find initial speed means u, okay. So half mu square is equal to minus g m e m by re plus h plus g m e m by re, okay. Now we can cancel m, and we know that we know that mass of the earth 6 into 10 to the power 24, 6 into 10 to the power 24 kg. We know already g, we know h is equal to, this is the h, 6400 kilometer, okay. So put here 6400 into 10 to the power 3, so that will give u square is equal to two into minus g m e by re plus h plus g m e by re. From here we can find u, okay. Already we know g, already we know me, mass of the earth. H is given 6400 into 10 to the power 3, okay. So everything is known, you can find here u. That's it, this part is completed.